Okay, let's get a little deeper into the signal production. Now, mind you, with every type of pulse sequence, this basic explanation that I'm going to give you for the signal production is going to vary. We're going to go down to the very most elemental components of an MR signal creation. Okay, let's talk about what happens to the proton when the patient's first put into the magnet. Remember, we have positively charged protons, we have negatively charged electrons, we have neutrons. And so when a patient, a human being, is put into a magnet with a strong magnetic pull, for the sake of simplicity, we're just going to say that all the positive protons of the hydrogen atom align with the z-axis or the longitudinal direction of the magnet, okay? Now, to disturb that state of equilibrium, we send in an RF excitation pulse, which is a radio frequency pulse. The purpose of the pulse is simply to shake things up, to disturb the protons, to knock things off of balance. Now, when we knock things off of balance in such a way that we flip that z-axis, that proton, into what we call the negative z state, or flip it, then we flip it into what's called the transverse plane, which is 90 degrees to the longitudinal plane. Now, these protons are still precessing, they're still wobbling. We talked about precession during the last module. But the moment that energy, that RF energy, is stopped, the pull of the magnet takes that proton back to the longitudinal direction, pulls it back to the z-axis of the magnet. Okay, so as this proton, now think about it again, it was pulled to the longitudinal plane of the magnet. The proton was in the z-axis direction as the patient enters the magnet. Then we sent in an RF pulse, an excitation pulse, which pushed it down to the transverse plane. Then, as soon as the pulse stops, what did I say? I said the proton starts going back to the z-axis or the longitudinal plane. During that time, when the RF pulse stops and the proton is starting to be pulled back into the longitudinal direction, free induction decay occurs. A radio signal is created by the protons, by the patient itself, as that proton is returning to the equilibrium or that z-axis. That signal is what we create our MR images off of. Well, I don't know about you, but I'm a visual creature. So what we're going to do is we're going to talk about what I just explained to you on the last slide through pictures. What I explained to you was called a disturbance. We took a proton that was pulled in the longitudinal direction. It was in a state of equilibrium. We disturbed it with an RF pulse. So let's look at what this looks like on a graph. First of all, we don't just get the RF pulse out of nowhere. It has to be turned on. When we turn it on, there's a ramping up, or what we call a slew rate. And that is how powerful, and that slew rates depend upon how strong your gradients are. Remember, we talked about 3 sets of gradients, X, Y, and Z gradients, 2 pairs on each end of the magnet, in the Z direction, in the Y direction, and in the X direction. So, looking at this graph, we're going to use this, which is a graph of a disturbance on a spin echo sequence. First thing we look at is our rise time, which is the time it takes for a gradient to reach its maximum strength. We're going to look at the amplitude, or the strength of the gradient over time as it's applied. Okay, so taking the same graph we were just looking at, the excitation pulse is represented by, it says RFT. The T stands for transmission. So that is a pulse being transmitted from the bore of the magnet, okay? So radio frequency transmitted, that's what that line represents. Now it says 90 degrees here. So what we're doing is we're taking the longitudinal plane, the proton that's in the z-axis in the longitudinal plane, and we're flipping it 90 degrees into the transverse plane. Now, if you notice the second row, it says RFR. It says that RFR stands for receiver. So, radio frequency receiver. Remember what I said, when we push it into the transverse plane and then when we turn the RF pulse off, what happens to the proton? It wants to go back to the longitudinal plane. And so as it's going back to the longitudinal plane, that's when the signal comes out of the tissue, out of the patient. And so we listen to it with a receiver coil. So the first row on your graph stands for radio frequency transmission. The second row on your graph is radio frequency receiver. Now the reason on your previous graph that I kind of imposed a trapezoid, a green trapezoid under the receiver is to represent the ramping up and the ramping down of that gradient. Remember, the slew rate is a relationship between the time it takes for the full rise of the power of the gradient and the full amplitude of the gradient once it is applied. A term you're going to hear in MR a lot is called your flip angle. Now the flip angle is the rotation away from the main magnetic field or the longitudinal axis. In our first graph that we've been showing you today, I've been using that first excitation pulse as a 90-degree pulse. 90 degrees represents how many degrees away from the longitudinal plane that the proton is flipped. The longitudinal plane, I'm using these terms interchangeably because you will see them interchangeably used. The longitudinal plane, the main BO, the main magnetic field represented by a capital B, a small subscript 0. The z-axis, all of these mean the same thing. So the degrees in which that proton is flipped away from this longitudinal plane represents your flip angle. A 90-degree RF pulse is the most common excitation pulse used. The amount of the flip depends on the RF amplitude and the RF pulse duration that we were talking about earlier. Look on this picture though. There's a very important fact I want you to notice. It doesn't flip in one direction. It flips in 3 directions. It not only goes from the proton does not only go from the longitudinal plane to the transverse, but once it's in the transverse, it spirals back up to longitudinal, and when it's flipping down, it spirals down to the transverse. This is very important. Remember the last module we talked about precession and wobble effect. This is not a one-dimensional flip from longitudinal to transverse back to longitudinal. It rotates down in a wobbling fashion and it wobbles back up to the longitudinal when the RF pulse is stopped. This is a very important fact of MR physics that you need to understand. It is when the RF pulse stops and this wobbling occurs back to the longitudinal plane that free induction occurs. The decreasing MR signal, which is received after the RF pulse is turned off, is called free induction decay. And it is that free induction decay, or FID, that is the basis of the MR signal. Again, let's try to paint a picture of this for you. So in this picture, the red line represents the pull of the proton into the z-axis, the longitudinal state, to the main BO of the magnet. Okay, so again, using those terms interchangeably. So this is how the proton is when the patient enters the MR environment. So then an RF pulse is applied, and the proton is flipped 90 degrees in this case, from the longitudinal plane into the transverse plane. As long as the RF pulse stays on, the proton will stay in this state, the transverse plane, also called the negative Z state. But what we'll find, as these pictures represent, when the RF pulse is turned off, the proton starts pulling back to the longitudinal state, to the main magnetic field, to the z-axis, however you want to refer to it. And while this is happening, signal is coming from the proton itself. That is the basis of MR imaging. The only thing you do not see in this picture representation is the wobbling back to the longitudinal state, because this is a one-dimensional picture on a PowerPoint. Okay, so we've covered the first column, I guess, of events that happen on the graph. We've covered the RF transmitter and the 90-degree excitation pulse, the RF receiver and its free induction decay. Let's move on to the actual rephasing pulse, which it is the rephasing pulse that creates the MR signal that we actually use through the Lamour equation. Okay, so once the proton has been flipped into the transverse plane and it relaxes back to the longitudinal plane during that excitation pulse, a second pulse is applied. This is your rephasing pulse. This is the pulse that we use to make the signal that actually goes through the Lamour equation. Now I'll tell you why we don't use the excitation pulse for our signal. So you have your proton pulled in the longitudinal axis. You've hit it with an RF excitation pulse to send it into the transverse plane, or what we also call the negative Z state. You stop the RF pulse, and immediately the protons start pulling back toward the longitudinal plane. Now the thing is, they all pull back at different speeds. Some are going to be pulled back a lot faster and relax a lot faster. Some are going to relax a little bit slower. The signal is only as powerful as the number of protons that are in line with each other during the echo collection. So the rephasing pulse, the purpose of the rephasing pulse is to get the different protons, quote, in phase with each other, so that when you choose to listen to your signal, which is your echo time, you have as many in phase with each other as possible to add to the signal collection. So imagine, look at this picture. These are pictures taken from Dr. Bouchong's book, and he drew these himself. You have the protons, 3 different protons at the start of the race. They all take off together during the excitation pulse. They're all spinning down into the negative Z state, or the transverse plane. When you hit it, they start to separate. When you hit it with a 180-degree rephasing pulse, you make them do an about face on the track. And so they haven't changed in speed. The slow one is still slow, the fast one's still fast, the fastest one is still fastest. But as they have done their 180 and they're coming back around the track the opposite direction, eventually, even if those speeds didn't change, they're all going to line up at one point. When you as a technologist select the parameter called echo time on your pulse sequence, you are telling the computer when to listen to the echo, when to acquire that signal from the protons. And depending on what that time is, the protons are going to be in phase with each other, out of phase with each other, have the most signal, have less signal. And all of these decisions will determine what the image will look like when it appears on your screen. So looking at it on a graph, we have now gone over the RFT, the RF transmitter. The 90-degree represented your excitation pulse, or that initial disturbance of the protons. The 180 degrees represents the rephasing pulse, and remember what that is. That the proton on its way back to the longitudinal state, as it's spiraling back in a loop formation, think about it as going around the track. The 180 turns the proton in the opposite direction on that track, but it's still being pulled back to the longitudinal state. Then with the second line there on your graph, you see RFR, the radio frequency receiver. What it is telling you is when there is a signal coming out of the protons themselves. At the same time as the excitation pulse, or that 90-degree pulse, you see FID, free induction decay. And what it's telling you is that there is signal coming from the tissue, coming from the protons themselves as that proton is relaxing back to the longitudinal state. Notice it's only half of a waveform though, because those protons are not in phase with each other. It's not until that 180-degree pulse is transmitted that we as technologists select an echo time that will correspond to the type of signal we want to see on the image, and then we acquire a full echo and listen to it. That's where the ear comes in, and that is the signal that goes through the Lamour equation and pops up on our screen as an image. Now you can see on the graph there's still 3 more lines we haven't even covered yet. All we've done is the transmit and receive line. There's still the slice gradient, the readout gradient, and the phase gradient that we haven't covered, and we're not going to cover for a while. Right now we're just talking about the basic signal formation. Okay, so let's look at everything on one line. Very, very basic. Start from the beginning to what we've covered so far. So the first thing that happens is a patient goes into a magnet. All the protons line up with the pull of the magnet, which is the main magnetic field. You will see graphically illustrated with a capital B and a subscript 0. It can also be referred to as the longitudinal plane, the Z state. All of these words are used interchangeably. Then what happens is we hit the protons with an excitation pulse, represented here with that 90 degrees. So we push the protons down into the transverse plane at that point. And they're spinning along the transverse axis in a big loop like a race car track or like a quarter-mile track like we saw in the runners. The moment the RF pulse stops, the protons start pulling back to the longitudinal plane. But they're all out of phase from each other, so there's no real good signal acquisition there. So what do we do then? We hit it with a rephasing pulse, represented here as your 180. A 180 degree RF pulse spins the proton around on the track so that the slow proton is now in the front, the fast proton's in the back, and they're still going at the same speed as they make their revolutions around the wobble as it goes back to the longitudinal state, or the z-axis. Free induction decay is occurring, which means that as the proton is coming back to the z-axis, back to the longitudinal axis, back to the main magnetic field axis, the protons are emitting signal out, so we get an echo. And then as we've set the time between the initial 90-degree excitation pulse and the time of the echo acquisition is one of those parameters that you as a technologist will set at your scanners. That's called your TE time, your echo time. I know it's weird, it's not ET time, it's TE time, but it represents your echo time. That is how many milliseconds from the excitation pulse to the echo acquisition. Now notice on this graph you see a 90, 180, echo. Then if you go a little bit further down the bar you see this little double slash time, which means let's start it again. Recycle, repeat, repeat it all over again. So guess what? The time from the initial 90-degree pulse to the time you do that initial 90-degree pulse for the second cycle, the second repetition, is called your TR time, your repetition time. Well, that's it for this particular study guide for Module 10. I do have some other assignments I need you to do on the website. I'm going to send you to IMUS to look at some of these same signal production elements under the IMUS website. I have some stuff I need you to read in the book. But you should be very proud if you've been able to understand these basic elements and see the elements as they transpire on the graph. If you can identify an excitation pulse on the graph, your rephasing pulse on the graph, your free induction decay under the RF receiver, your signal acquisition or your echo acquisition under the RF receiver, you have already accomplished so much. And these elements have been known to be on the MRI registry. It is one of those things that you only get unless you study it from a book. So congratulations, and I hope you've enjoyed this lesson.